viewers, welcome to Gurukul Live Lectures. Myself Dr. Preeti Chugwani. I am from Department of Computer Science, Aryabhatta College, University of Delhi. So here I am presenting you the another lecture in the series of data structures. So today's agenda will be heaps. So here we will discuss about heaps, and the contents of the lecture will be, I will be taking introduction to heap, explain in detail what heap is, that what actually is heap, then what are its type and applications, and how to build heap from an array. So these three topics in detail we will be covering in today's lecture. So consider a scenario that there are n jobs in a queue to be done. Each job is having its own priority. That priority is in the form of an integer. Higher the priority, that the higher priority job is to be executed first. So maximum priority job to be executed first, and along with that maximum priority job execution, at each point of time we need to take care of insertion of a new job into the queue, and that job is also having its own priority, obviously, because that is a priority queue of jobs. At each point we need to search the job with maximum priority and need to handle the insertion of new job also. For this task we can take the help from the data structure heap. In today's lecture we will be looking heap from the point of view of data structure. Please be careful that I am not talking about heap from memory point of view. I am talking about heap as a data structure. So this scenario of priority queue of jobs can be easily executed by using a heap, by considering n jobs as n nodes of the heap tree. The moment I say heap tree, the figure which comes into our mind is a kind of a binary tree, or more specifically a binary search tree. In the coming minutes I will be also telling that what is the difference between binary search tree and binary heap, and which to use when. So let's say we are having a tree of this sort, 6 5 4 3 2 0 1, in which in an array these are stored as the numbers as shown on the figure 6 5 4 3 2 0 1. So this 6 4 5 3 2 0 1 are having their own indexes inside the array. So what I am trying to say here, every tree can be simulated, or every array can be simulated using a tree. Now how to simulate an array into a tree? We need to store one element at index I, which is inside the array, and the name of the array I am assuming here is ARR, that is array. So we need to store one element at index I in the array, and its parent and index at the and its parent node will be having index I divided by 2, I by 2, unless it is a root, because we are aware that root is having no parent. Its left child will be stored at 2 into I, and its right child will be stored at 2 into I plus 1. So in this way we can simulate a tree, or you can say a subtree and an array. Now index of root will be 1 in array. If we want to take index of root as 0, then in that case we will be storing parent at I minus 1 by 2 instead of I by 2. We will be storing left child at the index 2 into I plus 1 instead of 2 into I, and we will be storing right child at the index 2 into I plus 1, 2 into I plus 2 instead of 2 into I plus 1. So the point is, here we can manage both the things, whether the index of root we are taking as 1 or whether the index of root we are taking as 0. Both are manageable with a simple kind of adjustments. So let's say we are having in this figure we are taking index as 1, it is having 6, 4, 5. That is the tree I have already shown you. Here I have just calculated the indexes. For 6, index is 1. For its left child, the index is 2. For its right child, the index is 3. And similarly, for the left child of 4, the index is 4. The child is 3. 4 is having its right child as 2 and its index is 5, while the index of left child and right child of 5 are 6 and 7, which are calculated by using simple formulas. Here, as you can see on the screen in the array, that we have taken root as having index 1. We have not taken root as having index 0, but that can be taken, as I have already told you, that with simple, some adjustment. We can take 6 and then 4, 5, 3, 2, 1 by adjustments. So, now coming to the previous scenario, I need a priority queue in which the operations which are to be performed are insertion of a particular job which is having its own priority, then deletion of a job with a priority. Let's say we want to delete a job, then we need to extract the job with the maximum maximum priority, or we need to decrease the priority of a particular job. All these operations are required to be done in a priority queue in efficient time. Now the question here arises, why do we need this heap structure? Can't all these be done using the binary search tree data structures? Because heap is also a tree type data structure, but binary search tree is more specifically, as the name indicates, it is used for searching. Here the idea is to perform insertion, removal, or decrease priority, or to get top priority element in an efficient time. The idea or the focus is not searching. Binary search tree is best for searching. It is not very efficient for these insert, delete, extract max and decrease key operation. So coming to the original idea of heap, heap is basically a tree based data structure, and it should be a complete binary tree. That means in a particular level you cannot go to the level I plus 1 unless your level ith level is full. You cannot go to the right child unless your left child is completely filled. So we have to go in the sequence of top to down and in a particular level left to right. And these in this complete binary tree, arrangement of elements is done in a very special manner depending upon what kind of heap it is. If it is a min heap or if it is a max heap. In a max heap, the key present at the root node must be greatest among the keys present at all of its children, and this property must go recursively true for all the subtrees in that complete binary tree. Similarly, if we consider a min heap, then in a min heap the key present at the root node must be minimum among the keys present at all of its children, and this property will be recursively true for all the subtrees in that binary tree. Now consider the figures given on the screen. One is a min heap, another is the max heap. So min heap we are having 10 as the root node, then 15 and 30. So the tree which is lying at the root node 10, 15 and 30 is satisfying the min heap property because the root is minimum. Then considering the left subtree 15, 40 and 50. So 15 is obviously minimum, is the minimum value among the three, and 30, 100 and 40. So 30 is the minimum among the right subtree. So that is a minimum heap tree, and you can notice that this is also a complete binary tree. Considering the right side figure in which the root node is 100. So now root node 100 is greatest of all the nodes available in the whole tree. Coming to the left subtree 40, it is greater than 10 and 15, and coming to the right subtree root is 50 and the children are 40 and 30, or 40 and 50 it could be, then in that case also it is greater than or equals to all of its children. So these are the two heaps, min heap and max heap. So summing up the applications, what are the applications of a heap data structure? A heap data structure can be used for sorting techniques, which is mainly known as heap sort. Although quick sort is a better idea of having sorting the elements, but heap sort can also be used at some places depending upon the application areas. Then we have priority queue, as I have told you in the starting of the lecture, that queue with queue of jobs or queue of tasks to be done, in which each and every task is having its own priority. That is what you call the priority queue. Then you have scheduler, for example CPU schedulers or some job schedulers. In that particular cases also the jobs or tasks are having their own priorities. Then these heap data structures can also be used for order statistics. Order statistics is nothing but finding the kth smallest or kth largest element in an array. Order statistics can be calculated very efficiently using the heap data structure. Apart from that, this heap data structure are also used in graph algorithms like Prim's algorithm. Prim's algorithm is an algorithm to find MST, minimum spanning tree of a graph, or if we want to find a shortest path from one node to another in a path. In that graph algorithms, in that category of graph algorithm, we have one very famous graph algorithm, that is Dijkstra's shortest path algorithm. So Prim's algorithms and Dijkstra's shortest path algorithm both are application areas of priority queues, and these priority queues are implemented using the heap data structures. So we can have variations of heap data structures. We can have binary heaps in which at most 2 children of a node are possible, or we can have Fibonacci heaps and binomial heaps, or we can have strict Fibonacci heaps also. But these Fibonacci heaps, binomial heaps and strict Fibonacci heaps are other variations of heaps which are used in some problems, but the most common which we use is binary heap. And in today's lecture we will be restricting ourselves with the explanation of binary heap only. Now let us consider an array, and now the idea is, or the task at hand is, to build the max heap, to build the corresponding max heap. So the task is to build a heap from an array, and we will be taking this problem with the help of a couple of examples. Now let's say we are having an input array which is 1, 3, 5, 4, 6, 13, 10, 9, 8, 15 and 17. These are the elements which are arranged, which are not arrayed. This is just an input array, and what do we need is the corresponding max heap. So corresponding max heap, if we as final output we need the tree with 17 at the root, 15 and 13 as its children. Now left key 15 having 9 and 6 as its children, 13 having 5 and 10 as its children, then 9 with 4 and 8 as its left and right children, 6 is having 3 and 1. So this type of a max heap is what is required from this input array. So in order to build the max heap from this input array, first of all, let us consider what is the difference between the binary tree generated from this array on the basis of index, which were discussed earlier, like I and I by 2 for the parent, and 2i plus 1 and 2i plus 2 for the left and right child. If we see the complete binary tree will look something like this. It is having 1, 3, 5, 4, 6, 13, 10, 9, 8, 15 and 17. This is the corresponding binary tree, but please notice that this is not a heap. This is neither the min heap nor the max heap, because the elements are arranged in a different manner. Considering the max heap, we need 17 as the rootmost node, and then 15 and 13 because these are the large trees. So this is just a complete binary tree with no heap properties. So our idea is to heapify the complete binary tree formed from the array. So heapify is basically an operation which is done on a particular node in order to ensure that that particular node and its subtree are following a particular heap property, whether it is the max heap or the min heap. So if we are talking about max heapify, we need to build the max heap. If we are talking about the min heapify, we need to build the min heap. So heapify is to form a complete heapify. We need to heapify the complete binary tree formed from the array, but this is to be done in a reverse level order following a top down approach. Now here arises a question, why this is to be done in a top down approach or in a reverse level order. I'll be answering it in the coming couple of minutes. That is, we need to top down approach means we need to first heapify the last node in the level order traversal. Then we need to heapify the second last node in the level order traversal, and so on and so forth. So basically, considering this complete binary tree which is shown in the figure 1, 3, 5, 4, 6, 13, 10 and so on and so forth, if I am talking about that I need to heapify the tree in a reverse order or in a top down manner. So here we are having 11 nodes in all, and please notice that all the leaves, that is 13, 10, 9, 8, 15 and 7 are considered as individual heaps. That means we essentially need not to perform the heapify procedure on these leaves. So last non-leaf node index is 11 by 2, which will be n by 2 minus 1, 11 by 2 minus 1, that is 4, and the last non-leaf node is 6. So to build the heap, we only need to heapify 1, 3, 5, 4, 6 and that too in reverse order. 13, 10, 9, 8, 15, 17 we need not to heapify. Now how to heapify? Let us consider it one by one. Here we want to heapify 6. In this case we need to swap 6 and 7. So the earlier complete binary tree which was formed using array is shown in the figure, and on the right hand side we just swap 6 and 17. Now considering the last level order traversal, last subtree of this tree, which is 17, 15 and 6. Now we can say that yes, it is a max heap because the root, which is 17, is greater than its left child 15, and it is also greater than its right child 6, and this we have attended by swapping 6 and 17, and this process is what you call heapifying a particular element or a particular node. So here we have heapified 6 by swapping 6 and 17. So what is the procedure? The procedure says within the subtree you take the root and then compare it with the left child as well as the right child both, and the key which is largest among the three should take its place at root node. So this is what has happened in swapping of 6 and 17. Coming back to the next node, which is 4. Now 4 is having 9 and 8 as its left and right subtree. So left and right subchild. So 9 we are just swapping with 4 because that is the greatest among all the three. So the immediate task at hand is to heapify 4. 4 is the root of a subtree which is having 9 and 8 as its left and right child respectively. So in 9 and 8 and 4, it will be compared with 4 will be compared with the other two left and right children and the key which is greater. So for example, here the 9 is the greatest among all will take place of the root. So here we will be able to heapify 9. Now please notice that as we have just started and the left and right subchild at present are actually the leaf nodes, so that's why heapifying the root node is not disturbing the left and right subchild. So this is also a possibility that the moment you heapify the root node of a particular subtree at level I, then at level I plus 1 it is its left and right subchilds are getting disturbed from its own heapify, from their own heapify property. So that has to be taken care of. I will be covering this example in a moment. Now the next task at hand is, as I have already told you, that we will be going level by level. So the next task is to heapify 5. So initially we have heapified the 6, then we have heapified 4. So the last two subtrees in the tree, in the considered tree, are heapified completely, and now we are moving on the level above and we are going in the reverse order. That means we are not going from left to right, we are going from right to left. So now we need to heapify 5. So 5 is having 13, 10 as its left and right subchild. 13 is the maximum, so 13 is going to take the position of root of this subtree. So 13, 5 and 10 we have heapified 5, or the node 5 has been heapified without disturbing any other heap property. So here now the next step says we need to heapify 3, which is the left sibling of 5. Now in order to heapify 3, we need to compare it with its two children left and right, which are 9 and 17. So what is needed to be done? We will shift 17 on the position of 3 and 3 will take position on 17. So what will happen? So here 3 as the root of the subtree having 15 and 6 as its left and right subtree, left and right children. So now this 3, 15 and 6 is having no heap property. That means the moment we shifted 3 and 17, the heap property of the rightmost subtree is being disturbed. So we need to again heapify that. Now we have 3, 15 and 6. Then in order to heapify 3 on that particular position or on its new position, we need to shift 15 onto the position of 3 and 3 onto the position of 15. We need to swap them. So this can be done in two steps. Firstly, a swapping of 3 and 17, and then a swapping of 3 and 15, and the final tree after this particular step will be in the correct heap property. So that's what I was saying, that in order, as we are moving up, in order to heapify a node at I plus 1 level, this is a perfect possibility that we are going to disturb the lower levels. So we need to escalate, or we need to, in programming terminology if I call, we need to take the steps of the heapifying recursively also. So we have heapified 3, and now we need to heapify a root node, which is heapify 1. Now this will also be done in 3 steps, as you can see on the screen. That 1, when swapped with 17, is going to disturb the left subtree of the root. Left subtree of the root will become 1, 9, 15. Then we will swap it with 15. Then 1 will take the position of current 15, and then 3 and 6 will be the left and right child of 1, the node 1. So what is happening here? 17 will take the position of 1, then 1 will percolate down to the position of 15, and then again 1 will again percolate down to the position of 6. So basically 3 steps, 1 onto the second level, then 1 will come onto the third level, and then 1 will come onto the fourth level, because one swapping is going to hamper the max heap property of the other subtrees, as you can see on the screen. So heapify 1 is done in 3 steps, and after these 3 steps, what are we having as the final heap is 17, 15, 13 as its left and right subchild, then 9 and 6 as the children of 15, 13 as the children of 5, 13 is having 5 and 10 as its children, 9 is having 4 and 8 as its children, and 6 is having 3 and 1 and its children, and all the subtrees including the whole tree are following the max heap property. And the array representation of heap will be a simple idea here, which is 17, 15, 13, 9, 6, 5, 10, 4, 8, 3, 1. This is the array representation of heap. Now let us take one more example, that is our example number 2 for building a heap from an array. So now the array which we are having is 4, 1, 3, 2, 16, 9, 10, 14, 8 and 7. So basically overall 10 element array, and the complete binary tree representation of this array as it is arranged is 4, 1, 3, 2, 16, 9, 10, as you can see on the screen. So what is happening here? How are we going to start? As I have already told you in the starting, that all the leaf nodes which are 9, 10, 14, 8 and 7, all leaf nodes are not needed to be heapified, because all leaf nodes are here single node heap tree in themselves, so they need not to be heapified. We'll start from the node 16. Comparing the node 16 with its child, which is 7, it is in a complete shape of max heap. So we need not to swap anything. Now, decreasing our index I for heapify, we will be taking the number 2. Now, number 2, that means the the index at the position number 4 is having its 2 children, which are 14 and 8. That means it is not a complete heap, max heap presently. We will swap 2 and 14. After swapping 2 and 14, we will go up to the level 3, to the next level, which is, now we will take up 3. 3 is having 9 and 10 as its left and right child. So 10 is the maximum element, and 10 will be swapped with 3, and 10 will take its position as root. Now, decreasing I further, I is the index on which we are actually operating upon. So, decreasing that index further, we are having the index 2 and the element present is 1. Subtree of 1 are having 14 and 16. So, we will be swapping 16 and 1. 16 will take the position of the current subtree which we are talking about, and 1 will take the position of 16. Now, just after this swap, what has happened, that the last non-complete subtree has lost its max heap property. That means 1 on the root and 7 as the left child. So, again we need to swap 1 and 7 both. So, this step is completed in 2 iterations. So, this is done in the way as it is shown on the figure. So, 16, then 7 and then 1. Now, our new index I for heapifying is index number 1, and the position is the root node, which is 4. Now, 4 is having 16 and 10 and as its children. So, 16 will be swapped in the position of 4 because that is the maximum one, and then 1 when take the position of 16 will destroy the heap property of its own subtree. Now, again it will take the position of 14, and 14 will take the position, the index 2. Then again we will be having 1, 2 and 8 at the positions 4, 8 and 9 respectively. So, again this is not the max heap, and then 8 and 1 will be swapped again. So, the element 4 which is present at 1 will be percolate down to the last level, first by swapping it with 16, then by swapping it with 14, and then by swapping it with 8. So, in the 3 iterations or in the 3 step, 4 will take its own place, and now the tree which is shown on the screen is having 16, 14, 10, 8, 7, 9, 3, 2, 4, 1 according to the level order traversal, and this you can see is a complete max heap. So, what actually we have done? We have max heapified each and every node. So, max heapify essentially says, if you are given a tree that is a heap except for the node I, max heapify function arranges the node I and its subtrees to satisfy the heap property or the max heap property. Now, in case of max heap, we can also have min heap. So, min heap is another variation or another type of heap data structure in which a tree that is heap except for the node I min heapify function will arranges the node I and its subtrees to satisfy the min heap property. Min heap property says root node will be minimum among all its among the whole tree, and this property will be percolated down recursively. This will be recursively true for all of its subtrees also. So now let us take a look for the code of the max heapify function. So now we want to max heapify. In this max heapify function or in this max heapify code, we need to we need to pass two parameters. One is the array I and another one is the index I, which we need to heapify. Now please remember that heapify is only working, one iteration of heapify is only working for one particular node. So now that node or that index is I, and now we have calculated its left is equals to left of I, as you can see on the screen, and R is equals to right of I. So this left of I and right of I are actually nothing but the functions in which formulas of calculation of index of left child and the calculation of the index of right child are encoded. So L is having the left index of I, R is the right child index of I. Now if L is less than A dot heap size and A of L is greater than A of I, largest is L, L largest is I. What does this code actually mean? This two-liner code of if and else actually means that for the heap size we are comparing the root node with the leftmost node and we are finding the largest among them, and in the next line when we say if R is less than equals to A dot heap size and A of R is greater than A of largest, largest equals to R. Here after finding the maximum between left and the root node which is stored in the largest, what we are doing, we are comparing that largest with the A of R, which is the right child of the R, and then we are replacing the largest node among the tree onto the root position or onto the ith position. So basically in this code up till now, what are we doing? As you can see on the screen, first we have taken the left index of the node I, right index of the node I, then we have compared that particular all the three elements of the subtree under consideration, that is the root node, left child and the right child, and we have taken largest among them. Now we are comparing if largest is not equals to the root thing, then we need to exchange AI and A of largest. Whichever is largest is going to take place at the root of the subtree. Now this is we are done with one with the heapification of one particular node. As you have seen in the example that this heapification may disturb the heapification property or heap property of its subtrees, then we need to recursively call this max heapify again on for the next the levels down, which are, you can say, so max heapify A comma largest. So now your largest is at the position which you need to heapify again recursively. So in order to heapify one subtree properly or in order to heapify one node properly, we may need to call this max heapify again and again. So max heapify A largest will take care of this, passing this largest value as the parameter of max heapify will definitely take care of how many times this max heapify has to be called. And one thing more, we have already taken a parameter if L is less than A dot heap size. So that means this will not go in an infinite loop of having of taking the nodes down the heap, down the leaves of the heap. This will take care of the size. L less than equals to A dot heap size, R less than equals to A dot heap size, and max heapify A of largest or A comma largest is going to take care the size constraint. So this was actually the manner in which we have taken the max heapify code. So in order to build the whole max heap, we need to call this max heapify for each and every node. But remember, each and every node is not what we need, because I have already told you initially that all the leaf elements are max heaps already. Then we need not to call max heapify on those nodes. So in order to construct a max heap, we need to start the last node that has children, and we need to go till to A dot n, which is to the root element. So the last node that has its children will occur at A dot length by 2. This will be the all the elements of the array which are not having its, which are actually leaf elements not having its leaf. So what I am trying to say is, leaf elements we need to skip. We need not to call max heapify for leaf elements, and we need to iterate back this max heapify to the root by calling max heapify for each and every node, which ensures that max heap property will be maintained at each step for all the evaluated nodes. This step or this caution has been taken care within the max heapify code. So in order to build max heap, the code of the function build max heap will be, we will be just passing the array inside the build max heap. Now it is going to take heap size as the length of the array, and then it will start from A dot length by 2. That means half of the length down to 1. Half of the length down to 1 essentially means we are just discarding, we are just skipping the leaf nodes. We are not taking the leaf node within the consideration of max heapify, because that we need not to, and half of the nodes in a top down in the bottom up manner we are going to the index number 1, which is the root. So for I is equals to A dot length by 2 down to 1, we need to call max heapify A comma I. So this is going to call max heapify for all the nodes starting from half of the length to down to the root. So in this way we can completely settle down with a array by building its corresponding max heap. So whatever max heap or max heapify build max heap property I have told you, that can be essentially done for min heap also. In the case of min heap, we will be min heapifying, and instead of finding the largest of the three elements which is the node, left child and the right child, we will be finding the smallest, and it is going to be attained within a very kind of just by changing some symbols of less than to greater than, we will be finding the smallest of all three, that will take place its root, and that will again percolate down to its lower level till the leaf node. So min heapify can also be done, and by calling that min heapify for half of the nodes as we have done in build max heap, that build min heap can be also done. So now let me summarize the lecture. So we have first of all we have seen a particular scenario in which we need a priority queue. That priority queue will be implemented with the help of heap by settling with the need of the heap as a heap within a heap as a data structure. We have taken a formal introduction of the heap, then have gone through its application and its type, and then we have seen how to simulate an array and a particular array to a tree. What are the differences between a complete binary tree which is following just a level order cell of the array and the heap, and then how to build the max heap by calling the function max heapify, which is taking a particular index and calculating the maximum element among the node, which is the index, the node, the left child and the right child, and that max heapify is to be called again and again for half of the nodes in order to build max heap. Hope you have enjoyed the lecture. Thank you for a patient hearing.